All right, let's start talking about related rates. Hopefully that won't close out again. And by that, what we mean, we're going to look at dy dx. We're going to go back to thinking about, dy dx represents slope of the tangent, right? If we're talking xy equations. But we also said that the derivative is rate of change. It's the rate of change. And that's where we're going with this one. Dy dx, dy dx is the slope of the tangent. So dy dx is the slope of the tangent. But in all other terms, if we're talking about rates of change, how could we say that with dy dx? Isn't that the rate at which y is changing? So it's the rate of change of y with respect to x. That's another way we can think of it. Right? Didn't we? You with me on that? Okay. So we're going to think in those terms now again. Okay? But here's another thing. Another thing. If t is the time, which we're going to be dealing a lot with t here now next, what about dy dt? What is dy dt? Well, we still are talking slope of tangent, but since we're not doing dy dx there, it's dy dt. Let's think about it in terms of this rate of change. Wouldn't that be, how would you state that as we stated above there? Dy dt would be, it's still the rate of change of y, but it's with respect to t. Yes, with respect to time t. So dy dt is the rate of change of y but with respect to t, time t. And for reasons that we shall soon know, we are going to be doing a lot of, with respect to t, derivatives. All right, now here's another little thing. We will then talk about this. Not to blow your mind anything, but couldn't we do a dx dt? Yep, we're going to be able to do dx dt's, which usually we're used to seeing the x with respect to doing the derivative with respect to x. But here we're doing the derivative with respect to t. So couldn't we do that? Yeah. And so guess what dx dt means? It's the rate of change of x with respect to t. All right? Okay, so here's what that means. And so, on B, ddt of 8y squared, what would you get there? Well, power rule, easy, be 16y, wouldn't it? But what else do I need? I'm doing the derivative with respect to t, and I'm doing it of a y expression. So I need a dy dt there too, don't I? Just like I needed dy dx previously, I'm going to need a dy dt. Okay? Because I'm doing the derivative with respect to t now. Okay? So I need a dy dt with that as well. All right, what about ddt of 7x cubed? You know, before we had an x one, we just had to do 21x squared. Well, we're still going to do 21x squared, but what else do we need now? Since I'm doing the derivative with respect to t, don't I need a dx dt? Yes. So that what you're doing the derivative with respect to, that's really a big deal. I mean, you got to pay attention to it. You know, we go along and we're doing the derivative with respect to x all the time, but when you're doing the derivative with respect to t, you got to think about those things. Is that okay? So that's the change here as far as derivatives are concerned. We're doing the derivative with respect to t a lot. All right, but here's we're kind of building our way up to some word problems, but step by step. Okay, so here's C. If y equals 2x to the fifth minus 3, find dy dt, the rate of change of y with respect to t, if x is 2 and dx dt is 4. Now, one quick little note here. I could plug in, right now, I could plug in x to be 2 to that equation. I don't want to do that right here, okay? Because, among other things, you know, the x value, I could choose x to be 3, and if I choose x to be 3, it's going to change my y value and things like that. So don't plug in x to be 2 yet. Until, since I'm trying to find dy dt, guess what I'm going to have to do here to both sides? Am I not going to have to do the derivative with respect to t to both sides? Yeah, d dt both sides here. Okay, so I'm going to do the d dt of the left, so that'll be the d dt of y. And then I'm going to do the d dt of the right side, so that's going to be the d dt of 2x to the fifth minus the d dt. Those are separate things there. They're just the minuses between them, so I can just do the derivative separately like that, right? There's no real rule to contend with. So what do I get? What's the d dt of y? Well, y, the derivative would be 1, but I'm doing the derivative with respect to t, so don't I need what else? dy dt? Just like before I needed dy dx, here I need a dy dt. Okay. What about d dt of 2x to the fifth? Well, that's 10x to the fourth. But now I'm doing the derivative with respect to t, so when I have a thing with x, doing the derivative of the thing with x, and I'm with respect to t, what else do I need? dx dt. And then the nicest one of the bunch is, what's the d dt of 3? 0. Okay. All right. Now, as you can see, I've got two derivatives present there, but that's no big deal here because here's what I'm trying to find. Go back to what I'm trying to find. I'm trying to find dy dt if x is 2 and dx dt is 4. Can I do that now? Here's dy dt. I can just say this is dy dt equals 10. I know x. I'm plugging in x to be 2. So it'll be 2 to the fourth. I know dx dt is 4. So I can just plug those in. dy dt turns out to be 10 times 16 times 4. Is that 640? dy dt is 640. So yeah, we're looking for numbers now, quantities. And we'll see what those mean in the context of some problems later on. Question or concern? So far, so good? How many homeworks? Not a whole lot. You don't have to have a whole lot to keep you occupied. Okay. The trig functions? I don't think so.
I hate those with a passion.
All right, let's go to D. Yeah. All right, D, we have, if y squared minus 5x squared equals 16, fine, same deal, dy dt, if x is 2, dx dt is 10. Okay, well, same thing. Again, what's the first step here? The first step is not substitution. I don't substitute, so again, let's make note of that. If you can learn that now, it'll help you later on, okay? Don't substitute yet. First. Okay. Because if you substitute first, you'll run into some problems. So let's don't substitute yet, because I'm looking for dy dt, and I've got dx dt. So what's the first step? First step is d dt both sides. So a d dt the left, so that'll be the d dt of y squared minus the d dt of 5x squared, won't it? And then the d dt of 16. Well, let's just go ahead and put that 0. So the d dt of y squared would be 2y dy dt. And then the d dt of 5x squared, so it'll be minus 10x dx dt, won't it? Equals 0. Now we can substitute. Once your d dt, now we can sub those things in. Got dy dt I'm looking for. The x is 2, so I have 2y dy dt minus 10 times 2 dx dt. So I have 2y dy dt minus, what was that, 200? Equals 0. Okay, what am I trying to find? Dy dt. I still have a problem though, don't I? That I didn't encounter before. What's the problem here? I still have a y. Do I have a y up here? It doesn't tell me a y up there. So this is a problem. How do I fix the problem? Aha, okay, so to find out what y is here, I'm going to have to go back to the original, find the value of y, go back to the original equation, and substitute x is 2. So I'm going to plug in x to be 2. Since I need y, I'm going to substitute x to be 2 right here. So it's going to be y squared minus 5 times 2 squared equals 16. And so I get y squared minus, be 5 times 4 would be 20 equals 16. Yeah, so I can figure out the y value. Even though it wasn't given to me, it does have a value because x is 2, tells me it has a value. So it'll be y squared, add the 20, so y squared equals 36. And so here, actually, without any other parameters, what could y be? Plus or minus square root of 36? Plus or minus 6? Okay. So that's what I can plug in. 2, and I don't think it'll make a whole lot of difference if I do plus or minus. So if I do plus or minus 6 here, let's do it both at the same time. You can do them separately if you want. So I'd have plus or minus 12 dy dt minus 200 equals 0. And so to, what's that going to be? Move the 200, so I have plus or minus 12 dy dt equals 200. So divide off the plus or minus 12. Okay, so dy dt equals, what would that be, plus or minus, let's see, it reduces by 4, be 50/3. So you've got a dy dt of 50/3 or a dy dt of negative 50/3. depending on the y value that you take there. Okay? All right. All right, got one more, working our way up the chain here. If z squared equals x cubed plus the square root of y, find the rate at which z is changing when x is 2 and y is 9 and dx dt is 5 and dy dt is 3. Okay, just added a z into the mix. All right, so what am I looking for here? It says the rate at which z is changing, but am I just looking for z? No, I'm not looking for z. I'll have to think about z, but what am I looking for? What does this mean? What quantity is that? The rate at which z is changing. Because really, when we get to these word problems, it's not going to say find dx dt or dy dt. It's going to have words. What am I looking for? I'm looking for the rate at which z is changing. That's dz dt, yes. That's what I'm trying to find. Okay, so doesn't that mean I need a ddt, all these things in this equation here? All right, so dz dt everything. All right, so ddt everything. So ddt of z squared, ddt the x cubed, and ddt the square root of y to the 1/2. What do I get? So that would be 2z dz dt. That would be ddt of x cubed would be 3x squared dx dt. Plus then the ddt of y to the 1/2, that'd be 1/2 y to the minus 1/2 dy dt. So I've got x, y, and z. I'm doing the derivative with respect to t, so each one of those parts has a ddt in it. dz dt, dx dt, and dy dt respectively. With me? Okay so far. So now I've ddt'd. Now I can substitute. Once you ddt, you can substitute. However, I have a slight problem. I've got x is 2, y is 9, dx dt. What else do I need? I've got x, I've got y, I've got dx dt, I've got the dy dt. I still need z, don't I? How am I going to get z? Well, to get z, go back to the original equation. Just like we did a while ago for y. And substitute your x is 2, your y is 9. So I'm going back to z squared equals x cubed plus square root of y. So now I know if x is 2, y is 9, so it'd be square root of 9. So z squared equals 8 plus 3. So what's z? Z squared equals 11, so z is plus or minus the square root of 11. And make it a little easier on us, let me add one more thing here. Z greater than 0. So that'll just get rid of the negative. All right, so let's just say z is square root of 11. It may say that, it may not. You can do the negative square root of 11. Throw that in the mix there. All right, so we'll go with 2. Z is the square root of 11. dz dt equals 3x squared. Well, x was 2, wasn't it? X is 2. What's dx dt? Whoops, wrong way. Too much. dx dt is 5. Right there. Then we have 1/2 plus 1/2 y to the negative 1/2. Y was 9, so it would be 9 to the negative 1/2. And then dy dt is 3. If we can decipher all that, we can figure out what dz dt is. That'd be, what, 3 times 4 times 5 would be 60. Plus, that would be 1/2. 9 to the negative 1/2, isn't that 1/3? It's 1 over 9 to the, it's 1 over the square root of 9, isn't it? So that's 1/3 times 3. With me on that? I do all that right. So I've got 2 square root of 11 dz dt equals, well, the 3's cancel, so that's 60 and a half, 60.5. And so divide off the 2 square root of 11, and there is your lovely value of dz dt. 60.5 divided by 2 square root of 11. And a lot of times they will want a decimal answer on that, so let's just round that off to one decimal place here. 60.5 divided by 2 square root of 11. I get 9. Try that again. 60.5 divided by 2 square root of 11. So 9.12, 2 decimal places. Okay? So the rate of change of z at this particular, for these particular values. That's what we were looking for. We wanted the rate of change of z when x is 2. All right. So that's my rate of change of z. Okay? All right. Well, let's